All right, hey everyone. Thanks for coming back from the snacks for this. This is a talk on volumetric neural style transfer for Fire on Elemental. In earlier talks, I saw AI was listed as an exciting topic, so hopefully this is exciting. Just sort of some context on volumetric neural style transfer. This is a technique that sort of has been around in the literature since 2019, the SIGGRAPH Asia paper on transport-based neural style transfer. And I got involved more around the 2020 timeframe. This is work from DisneyResearch, where we started evaluating applications for volumetric neural style transfer for feature film animation. Folks from Disney Animation and Pixar saw this research and wanted to give it a try. Now, volumetric neural style transfer is a mouthful, so I'm going to say VNST a lot in this presentation. And suffice to say, it's a way to take an image style and sort of imbue that style onto a volume. Note the work we did on Elemental sort of got published in the 2022 SIGGRAPH Asia paper. So I'm going to gloss over a lot of details. If you want a deep dive, I recommend checking out these SIGGRAPH papers. All right, so first let's take a step back. What is neural style transfer? This is actually a vintage or classic machine learning technique, and that goes all the way back to 2015. And that basically the idea is you have a content image and you have a style image, and you try to take something about the style of the style image and put it onto the content image. So you combine that smoke with that fake Van Gogh picture, and you got Van Gogh-y smoke was the basic idea. Problem is it only worked on images, and we want to use it on volumes. But it's easier to understand how it works on images first. So the way it works is you start with your picture of your smoke, and you run it through a neural network that has been trained to classify images. So this is a network that says you give it the picture of smoke, and it will say, hey, that's smoke, or that's cat, that's a dog. The label isn't important for this use case. What's actually interesting is the activations of the neural network layers on the way to that label. It's a convolutional neural net typically, so each layer is half the size of the previous one. And the layer with the most pixels, you might say those activations are like your fine-grained texture. Half that, maybe that's patterns, half that is parts, and so on. We call these things content features. When you take the style, you can then take the style image and run it through that same network, and then you have style features. The cross correlation between those features, heard it called a Graham matrix before, but basically that's the kind of thing that conveys style. What we do is we try to minimize the difference in style between the content image and the style image, and that's what sort of transfers the image. Now, I apologize, that explanation is not great. This is normally given by my colleague at DisneyResearch, but I'm trying to explain what's going on underneath the hood. But it's a fairly intuitive concept, style transfer, but what's going on underneath the hood is we're minimizing the difference of these neural network activation weights when we run both the content and the style through the same network. So this was first published in 2015. So again, this is vintage. Here's the algorithm for doing it. What's new is that we're applying it for volumes. What does that mean? Well, we can't just change pixel colors. It doesn't actually look terribly good. If we go back to that earlier slide, that doesn't look like Starry Night volume. It just looks like you put a bunch of color on that smoke. To actually move the volume around, what we actually need to do is create a displacement vector field that pushes those voxels around until that smoke starts to have that style emerge from it. We actually do it through what we call a differentiable rendering. We actually take a bunch of cameras, we render that volume, we run those renders through that neural network to get those activation weights. We figure out, well, the style's a little bit different from what we want. How do we move the voxels around to better match the style? Because it's a differentiable renderer, you actually can go back all the way from the renderer to voxel locations and push them around a little bit to minimize. It's really neat that this actually works. And since this is all on a GPU, you can actually do many, many, many renders, every second and change values. And you basically just iterate 30 to 100 times until it looks correct. And yeah, this is sort of what it looks like. So here's the unstylized input. This is with a Fire image. You can start to see some, cusps and curves in there. This is painterly. It's a little brush strokey. Again, everyone uses Van Gogh for these demonstrations, and so on. So these were the early results that were pretty cool. One interesting thing about all these are all done from a single view. So it's all from the camera. If you were to move the camera around here, it wouldn't look very good. In fact, this is a demonstration of, on the left, single view. You can see it's sort of projected through it, but you can actually do it from multiple cameras and get a full 3D stylization of the volume, which is pretty neat. We call that OmniView mode. So that was all work that was published in the 2019-2020 papers. What was sort of new that we came up with recently was that it's a fairly expensive process to do all these renders and move the voxels around. You could actually train a neural network on input and output, many examples of having stylized volumes, and then that neural network can be applied to new volumes that haven't been seen to basically do that same stylization. What's cool about that is you could do it on patches of a volume, overlap them a little bit, and now you can run it on a volume of any size. So you can do this on massive simulations if you want. So here's an example of what the feed-forward version looks like, where we've trained a neural network. And the quality is very similar in that case. Not every style comes out well. This one didn't look great. You got these weird striations. But for many styles, the trained network approach worked quite well. And we're going to talk about where we use that on Elemental. And here's an example showing that you can take a super high-res smoke sim. I don't know, maybe at Weta this is not high-res. This is 600 by 1300. But for us, this is pretty high. And then, you can see the stylization. All right, so how did we use these on Elemental? One of the things that was very challenging about the film is that, we didn't want our characters to sort of look like Ghost Rider or Demon. Like, we didn't want the characters to look like real fire. All of the reference we got, we wanted our protagonists to look like illustrated fire. And when you actually draw fire, it doesn't look like real fire. You have these kind of cusps and curves that anyone has ever tried drawing fire. Intuitively, you'll draw them. But that is not what we see in real pyro simulation. So we thought this was a good application for style transfer, where we can take those features from these intuitive 2D drawings and see if we can put them onto our 3D objects. That could also let us tune our volume simulations for performance and acting, not so much for their silhouettes and that kind of thing. So that's the goal. This was a very early test where we took this style image. We're calling it the fleur-de-lis image. It's not a fleur-de-lis, but I don't know what else to call it. It's this little swirls, and then this input pyro simulation. And then after we stylized it, we started seeing those cups and curves emerge from what looked like a very smooth and continuous pyro simulation. So this was an early test. There were a lot of artifacts and problems with it, but this was enough to start us down a multi-year process of seeing if we could apply this research to a production application on Elemental. So this is sort of where we ended up. VNST, this is how we applied it to the pyro simulation on Ember's head. Now again, if you look at that input on the left, that doesn't look like fire. And that's because we tuned the simulation for performance and acting, so it's more languid and fluid as opposed to like a roiling campfire. But when we apply style transfer, you start getting those cuffs and curves back. We use two style images here. One that, again, the fleur-de-lis, and the other one we call plume. And this is an example we can actually animate between one style and another. And you can see over time it starts out with the plume and then it ends up in the fleur. With the plume, the style image has a lot of points facing upwards, and that emphasizes maybe the buoyant nature of the simulation. Whereas with the fleur-de-lis, you have these curls and what looks like vortices. So the same pyro simulation could either look more buoyant or more turbulent, depending on which image. This actually allowed us to change characteristics of our fire post-simulation, depending on the character's emotions or what the situation was. You can also do mixes of both. We tried, this is an animation between that pair of the fleur-de-lis and the plume and a stripier version, and we started getting, more tendrils of fire emerge from that. You can even use style images that look nothing like fire. We use some swimming pool caustics on the right, and when we animate into that, you can see it starts to break up the fire a little bit in an interesting way. So there's a lot of freedom in which kind of style image you do. It might not have to have anything to do with the content. So here's how we used it in practice. On the left is Ember's raw pyro simulation before shading. And you can see it's pretty. Let me make sure you can see it on the monitor. I apologize if any of this is too subtle. But it's a little bit ghost-like. You know, as the pyro reaches the perimeter, it sort of just fades away with like a little bit of line work. And what we do is we displace it by the VNST vector field, and then we get those custom curves on the silhouette. And once we add the full shading to Ember, that's what we have on the screen right. Now this is the point where I need to be humble. This is by and large not the dominant feature of Ember's look. The hard-working effects artists and shading artists did really great work to bring her to life. VNST is just one step in the recipe for creating the look. That said, this was an important step, and we tried many other ways to do it. We could not figure out another way to get this look other than this technique. I'm sure there are ways to do it, but you know, I just want to say it is definitely solving a problem that we had trouble hitting otherwise. So that's VNST. In practice, here's how it looks in shots. These are the 3 style targets we ended up for Ember, the fleur-de-lis, a slightly modified version of that plume, another image we called dissipation. In the middle, you can see on top the raw pyro input, and then below the VNST output. And you can very much see those VNST shapes in the final look of Ember, even when her head is huge and fills screen. So it actually is it is a significant aspect of what's going on. Note that this is, I would say, a best case scenario. She's just hanging out in the center of frame. Of course it's going to work. What about when the camera moves? What about when she moves? Turns out it actually works. This is something we didn't know early on, was how well this would generalize to shots in motion. But you can sort of see that raw pyro input, even though the camera's moving and it's turning, it's totally fake. It's done for main cam, but the fire just seems to naturally evolve and you just sort of buy it. So we're very happy that, at least to the application of volumes, that even though it's sort of a main cam based technique, it still works under motion and shot conditions. Here's a little bit about, here's a more extreme example. So when Ember gets angry, we really emphasize the VNST, especially when she really, flames up there. And you can see, again, the raw input and the output, and you can very much see those custom curves in the final shot. A lot of before-after stuff. Left, no VNST. Right, VNST. See the results. All right, so we ended up using it primarily for Ember initially, but it was important enough to the look of fire characters. We started expanding its use to the other characters in the film. So these are some background characters where on the left was without VNST, on the right was with. And again, if you can, sometimes when I show this to people, they can't see what I'm talking about. So I'm going to try to make it super obvious. Hopefully you see the difference there. That's what the style transfer is doing. All right, so what else can you do with this? VNST has a lot of parameters in addition to just the style target. There's also things like tiling frequency. So basically, how large scale or small scale the pattern is. You can also modify the velocity inputs for how the pattern moves through the volume. And we found that we could actually, just by tweaking those parameters, control the perceived speed of the fire, even from one single pyro simulation. So in the center, you have your canonical Ember look. On the screen right, that's where we've doubled the input velocity, double the frequency, and it looks like the fire is moving faster. But it's the same fire. It's just the VNST is different. Same thing on the screen left. We've had the input velocity and have the frequency. It looks like the fire is moving slower. So we could actually control the activity of Ember's fire potentially per shot with these sort of techniques. In practice, where we used that the most was based on her emotion. It's actually her temper and her ability or inability to control it is a central theme in the film. So we worked really hard on giving a lot of visual cues to what her anger state is in the film. So angry is purple shading, more pyro fuel, more pyro noise, and then for VNST, 1.5x tile frequency, or tiling of the style image, and changing the ratio of which style images we're targeting. And that's sort of the recipe for Ember's anger look. And here's some examples of a bunch of shots where Ember is getting angry, and it's not just the same setting over the shot, it's sort of based on what's happening. And I apologize, I didn't get permission to share audio here, so imagine what's being said. But But yeah, you can definitely see VNST pretty clearly in these use cases. All right, so let's talk about other use cases. We had a lot of non-sentient fire in Elemental as well, including this ceremonial blue flame, which is sort of in the center of the fire shop where Ember lives. It gets seen a lot from all different angles. And unlike characters, this doesn't run through a per-shot process. It has to just be simulated once and then viewed from multiple angles. So this was a use case for the OmniView stylization. And to make that tractable for the larger voxel counts, we ended up using that trained feed-forward approach. And this is without NSD applied. This next slide is with it. And check it out. You can move the camera, and you can see that stylization applies in all 3 dimensions. Now, just to nerd out a little bit, one thing that's really interesting about this is this is done per frame with no velocity information, yet somehow, frame after frame, the style moves coherently through it. And this really surprised me. I thought we would have had to guide this, but somehow, because it was only ever trained on temporally coherent things, even if you run it frame at a time, out of order, it's temporally coherent. And that just, I didn't think that would happen. So that's one thing about machine learning is sometimes it just surprisingly works when you don't think it should. And this is a case where I was shocked that this happened. Doesn't work in every situation, but for Ember's fire style, it worked quite well. And here's how that looks in a shot. You can see how both the blue flame and Ember sort of have the same style, even though one is OmniView, one is per frame. We also used it for some smokestacks. This was a wedge that an effects artist did where they applied several trained networks in different orders to get different looks. And some of these are really weird, like the bubble version and things like that. We didn't use them all, but we ended up using a look like this to make there be more tendrils in the smoke so that it was a little less billowy. And this was even applied on wide shots, which I should have included in this presentation. And that's where we used the tiled inference to make sure we could handle larger voxel counts. All right, so how does this work and how expensive is it? This is could be a whole nother talk, but every fire character in Elemental went through a process called hexport, where we use Houdini to run a simulation, process that simulation, and then shade the voxels. That could actually take 300 minutes for a single character per shot. VNST was actually only 1 to 2 minutes of that. So it's a drop in the bucket compared to what else was going on. Problem was VNST used GPUs, not CPUs, and we do not have a render farm with very many GPUs. In fact, we have a render farm with 30 GPUs. And that was going to be an issue based on our back of the envelope calculation. So the systems team actually figured out a way to virtualize the GPUs we had on all of the artist workstations and use half the memory for what you're doing during the day and then half the memory for the render farm at night. So they don't need to log out of their computer or anything. They just have memory that gets hijacked by the farm. So that gave us an additional 150 nighttime GPUs. And that graph, the gray is the capacity, and you can see it oscillate from 30 to 150. And the purple was our actual use. And it's very intermittent, but you can see those huge spikes when all the renders get dispatched. So if we didn't have those nighttime GPUs, that would have flatlined and then slowed down all the render throughput. So that was super helpful. So thank you, systems, for virtualizing the GPU. So even though it was a fast process, we tried running it on a CPU, and it was like 90 times slower. So it was really worth going the extra mile to get GPUs working on the render farm. It says 1 minute here. Is that true? No, okay, just checking. Okay, cool. Just wanted to check. I'm almost done though. So for fire characters, VNST ran in 3 stages. We would write out a VDB file with density and velocity per frame. Then we'd write out a JSON that had all the animated VNST parameters. And then we'd run the stylization as a separate process because this is this run in a completely different software environment than Pixar's tools. So we had to have a Conda environment that got invoked, read the VDB files and the JSON, then write out new VDB files, and then we'd read those back in and move it along. So that's how we shoehorned it into our pipeline. Feedforward VNST was integrated on a similar way. So This is an open source forum, so here's my open source slide. OpenVDB, I want to give a shout out because that's really what made this handoff between the research component and the production component work. Originally, DisneyResearch was using 3D NumPy files, so these NPZ files with volume data, and they had these PySops in Houdini that were reading them in, and it was just miserable how slow it was, and they were huge on disk. As soon as we got DisneyResearch to start using OpenVDB, the data footprint dropped, the I/O was much better, and all the Houdini tools could understand the results. So that was a big deal. Other components of the software stack for VNST are, of course, open source as well. I wasn't able to verify I can talk about all of them, but OpenVDB, of course, happy to promote that we use that. And of course, a shout out to OpenUSD. We're increasingly, in our collaboration with DisneyResearch, sort of passing USD files back and forth, including USDZ, which zips it up so that you don't have dependencies on other files. And that's been a great way for us to collaborate with that team. So what's the future of this technique? It's interesting in that a lot of people think of this as NST as sort of like a Photoshop filter. You do your work, you apply the filter, you get something new. At some level, it can be considered that, but it's also a bit of a deeper art. And I just want to mention how that works. So at the surface level, if you've trained up these feed-forward networks where you have style in, style out, you can just plug and play on any volume. You either like the results or you don't, and you move on. You can stack them, several filters after another. But it's not super flexible, but we think that anyone can give that a try. But using the full VNST with the optimization framework, where you choose, the learning rate and the number of steps and the style images, that's a lot more complicated, but there's a whole lot more control you have. And I think that's where you get the best results. So you can make it easier by baking it down to a network, but usually, for the most part, we're running the full process. And then, of course, the highest level of skill. If you're actually going to train those feed-forward networks, that's a whole level of complexity you add on top of this. And so I just want to say, for anyone willing to explore it, there's different entry points to how involved you want to get. But it can get pretty deep. This is not necessarily a simple process, but I'm digging it. And we're actually expanding this technique to work with meshes as well, and then starting to re-explore the classic image case as well. So we think there's a lot with it. And so that's what we got. Happy to take any questions.
Any questions?
Hi, thanks. I saw when you were animating images, you're animating like from two pretty distinct images, like the floors or the peaks.
Yeah.
Did you experiment at all with, like, for example, like hand-drawn, like the actual hand-drawn 2D fire animation, like temporally coherent ones to get like the motion of like what a hand-drawn effects animator would do into it? Or is that possible with the pre-feed forward technique,
Yeah.
I guess?
It doesn't work terribly well, is what I found, in that, again, like I said, there's a subtle touch to this technique. So I found that it wasn't adding much to use like a completely illustrated ember versus a small swatch of just roughly the style to do that. There are some advances. This was using, again, that Graham matrix approach. There's another NST approach called Neural Neighbor Style Transfer, which only was published in 2022. And that's actually what we're using now for this technique moving forward, that more dramatically imbues the style. And then in that case, maybe it would have worked. Maybe there would have been more of a benefit from using the hand-drawn. But for this, just a swatch of roughly the pattern is basically going to give you the same thing as a fully drawn image over time.
Okay, thank you.
Cool, thanks.